So this is the fourth question related to application of Norton's theorem. So we have this circuit here. So we have to find the Norton equivalent circuit across these 2 points. Okay, we have to find. So first we have to find the Norton current. So we'll short these 2 terminals. Okay, 1 ampere, 6 ohm, 14 volt, 14 ohm, 3 ampere. Now when we short these 2 terminals, the 5 ohm resistor will go out because it makes no sense. The equivalent resistance will become 0 because current always takes the minimum resistance path. The shorted path offers no resistance, so current will flow through that, and this 5 ohm resistor will become of no use. It has no importance in this circuit. So we'll directly short the 2 terminals. This current flowing is IN. Now please pay attention here while we assign the currents to the respective branches. Here 3 ampere is flowing downwards, IN is flowing downwards. They will get added up to be IN plus 3. Here up to this point it is IN plus 3. Here 1 ampere is going out, so this will be IN plus 2. Here it is IN plus 3, here it is IN plus 2. Again 1 will get added up and this will become IN plus 3. The polarities like this. Again, another important thing, this 3 ampere current source lies in between these 2 closed loops. So this will become a super mesh when we apply the KVL equation. Okay, this entire thing. So now let us apply KVL to this whole mesh. Okay, this whole mesh. Now first let us start from here. 14 minus 14 into IN plus 3. Okay, there is no resistor here. Again minus 6 into IN plus 2 is equal to 0. This is the path. Okay, this. Okay, this 3 ampere current source lies in between these 2, so it becomes a super mesh. So this is the KVL equation. So we'll solve it to get IN. That implies 14 minus 14 IN minus 42 minus 6 IN minus 12 is equal to 0. That implies 14 minus 28 is 12, which is equal to this. 14 minus 42 minus 42 is minus 54. This is, and minus 54 plus 14 is 40, minus 40. So minus 40 minus 20 IN is equal to 0. That implies IN is equal to minus 40 by 20, which is equal to minus 2 ampere. This is the Norton current. IN is equal to minus 2 ampere. Okay. Now we have got the Norton current. Now we have to determine the equivalent resistance between these 2 points, deactivating the independent sources. So here we will open circuit the 1 ampere and 3 ampere current sources, short circuit the 14 volt voltage source. So this will become open circuited 1 ampere current source, this is short circuited, again this is open circuited, and this is the 5 ohm resistance. This is A, this is B, this is 5 ohm, 14 ohm, 6 ohm. 14 ohm and 6 ohm are in series. The series combination is in parallel with 5 ohm. So Rn will be 6 plus 14 parallel with 5, that is 20 parallel 5. It is 20 into 5 by 20 plus 5, which is 25, which is 100 by 25, which is 4 ohm. Okay, the Norton equivalent resistance, or the equivalent resistance simply between these 2 points, is 4 ohm. Okay, so here we have got the Norton current equal to minus 2 ampere, and this is the Norton resistance, equivalent resistance 4 ohm. So don't confuse with the minus sign. It simply means the direction which we have initially assumed with respect to the Norton current, whatever direction we have assumed in the circuit, it is simply the opposite of that. I have always told you, when we get minus sign with respect to anything, it simply means the direction which we assumed here, IN, not here actually, sorry, not here, okay, here in this circuit, this is not exactly this way, it was in this way, IN, okay, opposite direction. Suppose we would have assumed in upward direction and we got minus, it means it is downwards. If we assumed downwards previously and we got minus sign, it means upwards. This is the difference. So never confuse with the minus sign. It means the direction which you assumed, the original direction is opposite to that. Magnitude will stay the same. Okay. So this is the fourth question related to Norton equivalent circuit, application of Norton's theorem. Okay.